Here we are at section 11.3, where we will explore Kepler's laws. Our objectives here are to explain Kepler's three laws, including how they apply to planetary motion, identify and use the vocabulary associated with elliptical orbits, and also apply Kepler's laws to solve some problems involving orbital motion. Just a brief history on where these laws came from. There was an astronomer named Tycho Brahe who made very accurate astronomical measurements over the course of 20 years, followed planets, followed 777 stars, and Kepler was Brahe's assistant. He spent 16 years creating equations for the motion of the planets, and ultimately what Kepler came up with was he changed the heliocentric model with circular orbits to ones with elliptical orbits. He also summarized his work in three laws, which we will see in this section. And Newton was able to then go back, take a look at Kepler's laws, and prove or show that these laws were actually consequences of the gravitational force that he had explained with his laws of motion. Now, to begin, Kepler's first law was that each planet in the solar system actually moves in an elliptical orbit with the sun at one focus. So they were not circular orbits, but in fact elliptical. Like it said, the sun is at one focus and nothing is at the other focus. When you look at the geometry of an ellipse, basically the distance to the object, so like this would be the distance to one of the foci, and this would be the distance to the other one. The sum of these distances is always the same. So like if you took a string and pinned it down in these locations and then kind of stuck your pencil into it here and sort of dragged it around, you would end up pulling out a perfect ellipse. Now, there's some values that are interesting to note here that might be used. So first of all, the major axis. The major axis is this long distance through the ellipse, and that's a total distance of 2a, because if you were to cut that in half, that's what we call the semi-major axis, which is just a. The minor axis is the short way through the ellipse. That would have a distance of what we'd say is 2b, because half of that would just be b, and that's what we call the semi-minor axis. Now each focus is located at a distance c from the center. So if we were to put another distance on here, that's a distance c, and that's a distance c. So that the total equation of an ellipse is given by a squared equals b squared plus c squared. Another bit to understand about an ellipse is the idea of eccentricity. Eccentricity really just describes the general shape of the ellipse, how spread out it is. E would be equal to 0 for a circle, and we can see the equation for eccentricity here, and that's equal to c over a. So for a circle, that it would be equal to 0 because there wouldn't be any distance c from the center to the focus. But when we look at then high values of E, that would correspond to much longer, thinner ellipses. So we can see here an E value of 0.77. That is a much longer, thinner ellipse. When we look at this one here that has an E value of about 0.23, it actually looks pretty close to a circle there. Now when we look at some of the values associated with the planets, such as Earth, Earth has an E value of 0.017. Even Pluto, no longer a planet, would have an E value of 0.25. Now these are nearly indistinguishable from a circle, which was one of the reasons why Kepler's discovery was just such an accomplishment, to recognize that these were not in fact circular orbits. Now when we look at Halley's Comet, that's much easier to see. It has an E value of about 0.97, extremely long and thin, which means that it spends most of its 76-year period very far away from the sun. Now, when we look at some of the different positions that an object could be in relative to the sun, if it were orbiting the sun here, if we were to look at the point where you are farthest from the sun, that would be a distance a plus the distance c here. That position at the furthest point away from the sun is called aphelion. Now, if you were orbiting the Earth here instead of the sun here, we would call that apogee when you're orbiting the Earth, so the point that's the furthest away. Now, when you look at the distance that is closest to the sun, that would be when you are in this position over here, or a distance of a minus c. This is called perihelion, or again, if this is Earth that we were orbiting, we would call this perigee. So those are just some of the terms that you might see popping up in questions or things. When they ask a question when an object is located at aphelion or at apogee, you need to know that that means that you are working with the point that is furthest from the sun, whereas perihelion or perigee would be the points where you are closest to the sun. Now, for circular and elliptical orbits, those are shapes that are for bound objects. Bound objects meaning that they are bound to that gravitational center and cannot get away. So planets, moons, reoccurring comets, those things are not getting away. Whereas parabolas and hyperbolas would be the kinds of shapes that we would give to an unbound object. In fact, for an E value that is greater than 1, that's corresponding to a hyperbola. So those one-time pass-by types of deals like a meteoroid maybe. Now let's move on to Kepler's second law. Kepler's second law says that the radius vector drawn from the sun to any planet sweeps out equal areas in equal time intervals. Now you can see that very nicely in the diagram that we have here. What they're showing is that each one of these sections of this pie essentially are equal time intervals. And we can see that the shapes of the pie are all different, but ultimately what they're saying is that this area in here is equal to this area in here, and that the time interval to pass through them would be equal time intervals. So this can actually be shown to be a consequence of the conservation of angular momentum. Consider a planet that has some mass m sub p. It's moving around the sun in an ellipse. If we were to think about the forces that were acting on that planet, we would understand that the forces acting on that planet would be, in fact, gravitational forces. And of course, at any point in that planet's path around the sun, the direction of that force would always be, towards the center, whereas the motion of the planet itself would always be in sort of a tangential direction. So in terms of talking about torque and does that produce any torque, the answer is no, that does not create any torque, because these values are always going to be sort of perpendicular to each other. Now, if the torque is actually equal to 0, and when we studied chapter 10, we recognize that the torque could be set equal to dl dt, or the change in angular momentum over time. Now, if the change in angular momentum over time is 0, then basically what we're saying is that there is no change in the angular momentum, or L is conserved or is constant, meaning that this r cross p value is also going to be a constant. Now we could also look at this geometrically to see how it relates to these equal areas per time. In any time interval dt, the radius vector r is going to sweep out this little bit of area. We could call that dA. And that dA, that little bit of area that it's going to sweep out in here, we can see that that would sort of be like a slice of a parallelogram. If we were to, kind of create one whole parallelogram here, any little bit of time would sort of come through half of it, so that half of it would be swept out. So we could actually write that as 1/2 of r cross dr. Now we know that dr could be written as like a v dt, and when we write that out, we can put this now in a little bit of area, where that little bit of area can now be seen as this 1/2 times this r cross v dt, where again we know that a mass times the value of the velocity is going to give you p, and of course r cross p is angular momentum. So essentially, if we want to multiply by that m up top, we'd have to divide it out on the bottom too, and that's where we get this representation that we see here of that angular momentum over 2 times that mass dt. And again, what we're recognizing here is that this is just going to be a constant. It doesn't depend on time. And that's really all you need to gather from here, is that this is going to be a constant. dA dt is a constant value because that angular momentum is going to be conserved. Again, this is ultimately just a result of gravity being a central force, or always pulling towards the center of that orbit, and that's going to result in that constant angular momentum, and that would apply to any central forces. So here we are at Kepler's third and final law. Kepler's third law basically says that the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Now let's just quickly talk about where that comes from. This is actually really easy to see with circular orbits. Now imagine the sun here and a planet that was orbiting this sun coming around here. Let's say that this was a circular orbit. Now, if this was a circular orbit, then the force that's actually causing this thing to orbit would be the gravitational pull, right? There's a pull towards the sun or whatever it is that this is orbiting, and gravitational pulls can be defined in terms of their force. That force is equal to a gmm over r squared. Remember, that was Newton's law for universal gravitation, that force is equal to those two masses multiplied together divided by the distance between them squared, and that constant capital G. So that's the force that's actually causing this thing to move in this orbit. But again, it's causing it to move in a circle. So if this force is causing something to move in a circle, we know that F is equal to ma, where that a is now actually centripetal acceleration. So we could set this gmm over r squared equal to an mv squared over r. Now what we'll notice here is that we can cancel a couple of things out. The masses will cancel here. We can get rid of one of those r's that we have there. And for a circle, we know that the speed v is just going to be the distance around the circle divided by the total time it takes it to move around the circle once. Now the distance around the circle once would simply be the circumference, or 2 pi r. The time to move around the circle once would be the period of the motion, or capital T. So we can place that in here for our v squared. So I have my 2 pi r over t squaring that value, and then dividing that again by the r is still in there, but those will kind of cancel out again, you'll see. And so we just simplify this. And when you simplify this and actually get the t squared all by itself, go ahead and try it on your own if you want to. You'd find that you'd end up with this 4 pi squared over gm. And the m that we're left with here is the mass that the thing is actually orbiting. So that mass in the center that's really causing that gravitational field to be in play. And so when you simplify that down, you find that the square of the period is proportional to the cube of that radius, or that distance between the things that are orbiting, right? And ultimately out front, there's this constant. That's what we have this big capital K there for. And that big capital K is really just equal to the 4 pi squared over gm. Now, the same exact thing is true for elliptical orbits. We use the same exact constant k. It's still equal to 4 pi squared over gm, but the only difference is that instead of putting an r cubed in here, we're going to put an a cubed in, because again, this is not a circle. It doesn't have a radius. It would have that semi-major axis a. And so when we look at Kepler's third law, essentially you typically see it written this way, that t squared is equal to k a cubed. Now the constant k is actually independent of the planet's mass, whatever it is that's out here that's actually orbiting. And this would work for circular orbits, elliptical orbits, and it's valid for really any planet around the sun. And there would be a particular k value for any planet around the sun. You can actually look that up in your books and find that k value. But if you want to consider other things, so things other than planets orbiting the sun, you could look at things orbiting something else. For example, you might look at a satellite orbiting the Earth, or maybe a moon orbiting another planet. That k value is going to change. So you would actually have to plug in, again, the mass of that particular thing that it's orbiting into here to figure out what that k value is going to be for your new object that you're orbiting. If you actually take a look at table 11.1 on page 345, you'll see a lot of useful planetary data there that you can use as you begin to solve problems.